Hello, hello, hello. I'm Kevin Bourrillion.
I'm Louis Wasserman. Am I audible, or do I have to be closer? Okay.
All right, yeah, we noticed this mic seems pretty sensitive. So we are here to talk to you about some stuff we have been doing at Google to try to do our part to support Java language features. And so by way of introduction, by the way, we don't have a safe harbor slide. So whatever the horrific thing that's protecting against happening, I guess that's just going to be rampant now. I don't know what exactly is going to happen to us, but we don't have one of those. We work on core libraries and static analysis at Google. Out of curiosity, I'd love to know how many people in the room are familiar with what Guava is. That's excellent. So for the rest of you, it's just a bundle of our the core libraries. We work on a core libraries team. We release libraries for everyone at Google to use, and the ones that we are most proudest of, we open source those as Guava. Two other things we're involved in are Ericone, among many other people, some in this room, some not.
Liam, raise your hand.
Yeah, Liam. This is our static analysis framework. It also supports this mode called Refaster, which is very interesting. We're not going to talk a whole lot about it, but this is the basis for how we implement thousands and thousands of static analysis patterns at Google to steer developers toward better code. And yeah, Guava, I started Guava, I think about 11 years ago now, although it was never a one-person project. I basically write APIs in JavaDoc, and then other people come and fix all of my terrible implementation code and make it work. But another thing that we do, we're very commonly involved in guiding best practices and policy around Java usage at Google. So for example, I'm the primary but not only author of the Google Java Style Guide, which is out there on the web for you to see if you want it. The one thing that unites all of these things is that we are obsessed with trying to help Googlers' code be good code. My dream is I can pick any random, piece of source code in our company, and I look at it, and I'm like, yeah, that's the way I would have written it. That's the least code and the clearest code that it took in order to do that, and so everything we do is around trying to make that happen. The reason that we're here, we're going to talk briefly about a little bit of our experience developing Guava and how we use research into our own code base in order to guide those decisions. But the interesting part is to explore, this ability has been very, very exciting to us, and we want to see if there's ways that we can use it to benefit the community. And we've started to do that a little bit. I will say this slide, we're going to show a few examples. But this is more going to be, when I say explore this type of research, we're more setting up the question than we are answering the question, because all of this is still very new. We will share some examples of findings that we've already made, but even if you're not super impressed and wowed with those particular findings, the point is really to get everyone thinking about what else we could do to benefit the community with our data. So first thing we have to establish, what is this thing called Google 3? How many of you were vaguely aware that Google does this really insane thing with all of our source code? We store 95% of all of our source code in the same mono repository, and everyone basically builds and runs ahead. Some people were familiar with that. If you're not familiar with that, there is an ACM article. It is short, you can read it pretty quickly, but it's very interesting, and there's links to further things. It used to be, at first that information wasn't public. So when I was asked, I think I was asked on the Java Posse once many years ago, how much code are we talking about here? And I just had to say, well, if code were ice cream, it would be a lot of ice cream. That's the only thing I could say. But now, because this information is actually out, I can tell you we're talking about 2 million top-level classes totaling 300 million lines of code. That's the Java code base only. And if you can even read those smaller things there, those are the overall code base, and those statistics are 2.5 years, 3.5 years out of date, actually. But what it says is number of files 1 billion. So this is setting up the fact that we're talking about a lot of code. By the way, the reason it's called Google 3 for actually a very intuitive and a deep reason. The reason is because there was this thing already called Google 2. And I don't know, something went horribly wrong with it, and they had to start something new. Okay, so it's Google 3. There was briefly an effort. There were some people who believed that we needed to replace Google 3. You will never believe what they were going to call the replacement. Yes, they were going to call it Google 5, actually. We will not go into that.
So part of the experience of developing libraries when we're building in this context of this enormous monolithic repository is that we have to get down and dirty with our users' code a lot of the time. Among other things, there is continuous integration across the entire company. If we broke everybody and everybody builds against us at head, we would be rolled back without even automatically. And usually when we get people saying, hey, we want this feature, they can also point to exactly their use case without worrying about concealing any of the details. We get a link to a change, and they say, this code is awkward, I wish it could be better, hey, look at my specific example. So we spend a lot of time in general with the code being written against our library. And in the process of designing this library, our experience has been library design, like language design, can be contentious. There is a lot of debate, but it is rarely settled. Our design decisions have rarely been settled by saying, these are the pros and these are the cons of the decision. We're going to look at those, and one of these is clearly a winner. Usually, what decides, or what helps us decide a design decision, whichever. They're settled by the weights we assign to those pros and cons. And a lot of those weights, we've learned to figure them out and compare them by actually finding data, which I'll get into. These are some of the questions that we look for data on, and that I encourage you to think about, like whether these sorts of questions apply to decisions you are making. How much demand is there for this feature? So what we tend to do, we have this enormous code base that represents a huge variety of use cases. We'll discuss some of that later. But what we do is we look at how many people are already trying to solve this problem in the code base. And we actually have quite a lot of confidence that if there are people trying to solve a given problem in the code base, we can find them. That's some of the influence of the static analysis tooling that we have that we'll talk about a bit later. But we have a sense of if two users in the entire code base are trying to solve a given problem, it's not a very common problem. Or if it is, maybe it's a common problem not at Google. It's a problem we're not very well equipped to solve without having the insight of seeing more people solving this problem. But being able to see how many people are solving this problem we're trying to add an API to simplify lets us decide, is this worth a libraries level solution at all? Are existing alternatives difficult to use? Have we found ourselves building static analysis to say, hey, if you're trying to do this, don't do that, or this other thing, or this thing. And we can track, for example, how many times that static analysis fires. How many people are we having to tell, hey, you're trying to solve this problem, but you're getting it wrong in this particular way. We also have some research going on. This is a little ahead of things. Figuring out time to resolve. If there are errors that we can track people's development experience of how long it takes them to fix. Is there a subset of potential users that merit special casing? Once we have an enormous list of all of the places in Google's code base that are trying to solve this problem, are there any common features? How common is that feature? Is it a 99% of all the people fall into this special category? 75%, 25%, and that influences what we try to optimize for the use cases we think of when we're trying to look at alternate solutions. What does a proposed solution look like in the context of code that wasn't written specifically to demonstrate the feature? And relatedly, would the authors of existing code be pleased by a refactoring to use this feature? So we can have a sense of what is the actual distribution of what code solving this problem looks like. Does it look like the code that we think it does that we're trying to replace? And we can even like take a random sample or do a poll of authors of code that's trying to solve this one problem and say, would this API that we could add help you?
So being able to work in this manner has been an incredible experience and a real luxury. It's amazing to have like pretty much infinite insight into our internal users. And you know, those of you who are familiar with Guava may be aware that it's sort of famously difficult to send pull requests to. It's for reasons like this, that if we can't uncover the evidence in our own code base that it's needed, we feel like Guava is the wrong place for it. It should be, we don't want to pretend to be able to develop and own things that we aren't actually in touch with the need for. But what kinds of things, now that we have this ability to analyze this very large corpus of Java code, what other things could it be useful for? I'm going to answer that by answering the opposite question first. I just want to point out right off the bat, there's lots of things that this will never be useful for understanding. It's never, analyzing our code base is never going to tell you what general Java developers out in the world do across the entire world. One common, obvious example of this is we can't tell you whether people prefer spaces or tabs because at our company, you're going to prefer the spaces. We have decided that for you. But there are reasons why it's an interesting research corpus. The first, which we've covered, that it's very large. So the impact of this, if we're talking about, which we are going to later, analyzing switch statements, we're talking about 180,000 switch statements that we're analyzing. So that gives a lot of data, and it also means that if there's any kind of corner case that a person can do, it can be found in there somewhere. There's nothing so strange, that you can think of that we cannot find at least one match for in our depot, unless it's something that we have done the static analysis work to forbid as a pattern already. And this tends to be live, real live code, not prototype code that was written for a business reason in production. It tends to be deduplicated, which is a big challenge with slurping in code on the web. You never know how many different, which version of this should I accept. Everything in our repo is kind of one version only. And it all basically builds, passes tests, and uses consistent JDK and third-party library versions. It mostly uses consistent JDK and third library versions. That makes it a little more of a controlled environment to ask interesting questions. And we're going to see how it's readily analyzable at an AST level. The final point about what makes it an interesting corpus, I'm not going to talk through all these points individually, but it is not a depot where anyone working at the company can just check in whatever they want. There are many, many processes that stop them from just checking in whatever they want and stop us from checking in what we want to as well, I'll point out. There are at least 100 new types of compiler errors that we turn on. Nobody can build if you do this bad thing in your code. There are additional warnings that we send out as code review comments. There is the code review culture in the first place. And a culture of collective ownership and unit testing and so forth. All these things nudge the code base toward being more consistent and being,
in the direction of best practices.
In the direction of best practices, which is what we're going to. The reason why that's interesting, and this is a point that may make sense. One of the reasons that it is useful to study code that has been pushed in the direction of best practices to some degree is that when evaluating a new feature, you want to compare the value of the new feature against what the best code that people can do without the new feature is. That is certainly at least one of the things that you want to compare. That way you're not attributing any benefit to the new feature that is already benefits people could have just by refactoring what they already have. That said, this does not mean that our code base is already perfect code. It's not at all. But all these factors we just talked about that sort of move it in that direction make it one reason to be interested in data that we glean from it. So if there are benefits that are being claimed for a new language feature, but those can be realized in other ways, we have other avenues to do those things like education and static analysis and so forth. As a research corpus, it has a number of biases. Here are some biases we thought of to disclose. Of course, there may be others. Bias is everywhere. And, you know, our use cases are quite varied. You may know that Google gets into a lot of different things, but they're not as varied as all the world's code. For example, we have very few embedded or desktop apps. And a big one is that we have, you know, a difference between what frameworks are popular internally and popular externally. Some of our frameworks that are very heavily used internally are actually internal only. Some of them are released, like Juice, but we use it way more than the average person does. All right, given all those biases, some of you may be wondering, why are we talking about only analyzing our corpus of code instead of, hey, we are Google after all? Why aren't we here talking about slurping all the findable code on the web and analyzing that? That is a harder problem we haven't solved yet. Maybe we will. It's important to note that you're still going to get a whole lot of biases, and that result, they're just going to be different biases. It's going to be code, more library code than production application code, and so forth. So by being able to do research and share the aggregate results of our research, you're getting data from, you know, all of our proprietary code as well. We're able to harvest sort of meaningful statistics out of.
So talking a little bit about what we're doing here and how we're doing it. So we're operating in a context where we're working off of Ericone, which is our open source static analysis tool. And what that does is basically it's a relatively thin API atop JavaC's internal syntax tree. This is on the slide, a very simple Ericone analysis. It forbids people from writing throw null, which actually throws a null pointer exception because throw doesn't accept null. But we think that's very confusing if you did it, so you should write throw new null pointer exception instead.
And yes, some people were doing it.
It's true. So when we turn these on as compile errors, we're used to running a MapReduce over the entire Google Codebase. We take our suggested fix and we apply it as a refactoring to the entire codebase. But what we can do instead is instead of just outputting suggested fixes, we output data that we then collect and analyze and get interesting linguistic data off of. And this whole process takes us hours-ish, so we can do a fair bit of it.
All right, so we're going to show a few examples. I put a disclaimer here. I think that we have put a fair amount of work into getting good numbers here, but they are not yet, I have very, you know, they're not quite scientific numbers yet, and we might still revise them as we figure out some mistakes we might have made. Disclaimer over. So I'm going to pick just like this is a totally random, actually I thought we were skipping this. But you know what? We're doing well on. We're doing relatively well on time.
We're doing it now.
Okay, we'll start with this one then. What percentage of break and continue statements in our code base are labeled break and continue statements that point to a label? So I'll let you all guess in your mind what you think it is. This one, I think it won't be super shocking. Yeah, the answer comes out 1% of break statements. You can hardly see the red bar there. 1% of break statements and 0.4% of continue statements are labeled. But we wanted to drill into those, and there was this idea that came up. This idea for a very small language feature is not really an important part of the presentation, but it's an example of something where we said, well, here's a question we could get data to answer. So a suggestion came up on the Ember list at one point. What if, when breaking, instead of breaking to a label, you could identify which type of containing loop you were trying to go to? And on the screen here, we have an example of a loop that this would not work for on the left. Because you're trying, both of the containing loops are for loops. So if you had the ability to say break for, it would not go to the one that you mean. On the right, this one does work, because you can say break for, and it will pass up the while loop and go straight to the for. So immediately I wondered, well, if this feature existed, how often would we even be able to use it? And I think I might have even quoted a number on the list which was completely wrong. I made a serious error in my initial analysis because I accidentally included switch statements when I didn't mean to. There are many hazards to this work. So So let's see, everyone can think about what you expect this result to be. I think eventually, like if I do this in a bigger setting, I may run it as a real type of guessing game and have prizes and stuff, but I'm gonna I decided just now to spare you all of that. Also, I didn't bring prizes, so there's that too. Would you expect the proportion to be different for break versus continue, and what would you expect this proportion to be? Remember, it's the proportion for which they are breaking not to the immediately containing loop, but to the nearest containing loop of that kind. Well, okay, the slide already explains it better than I could. So, turns out it's an appreciable number, which is not what I first reported on the list. 42% of continue statements and 76% of break statements. So the point of this is not really like this settles anything about whether a language feature like this should be done, but it does, if the results had come back 2% instead, that would be a very different story, right? That would give us sort of some pause to wonder whether this was, you know, really going to be an interesting thing to even be thinking about.
All right, so another area that we just picked examples of the many analyses we've done to share with all of you, just to give you a sense of what sorts of data we can gather. So we did a lot of research on switches because there was discussion of expression switch and how that's going to work recently. These are not 100% representative of switch statements in the world. We'll discuss some of the ways in which they aren't in a moment. But we have 180,000 switch statements, and we think there's some interesting lessons to be learned from that many. So first question, do people put default cases anywhere but the end of the switch? This is honestly a feature that I'm not sure many people are aware of, a thing that you can do. You can in fact put the default as the first case of your switch. And it will check that it is not any of the later appearing switches. And there was a question, how many people actually use this? The answer, as you might imagine, is basically nobody. 0.3% of switches put the default first, 0.3% put the default somewhere in the middle, and the other 99.4% all had it at the end. This is about what you'd expect. Most people don't realize that can be a thing. How many switches would use case null if it were allowed? This is a tricky question. So what we searched for as a proxy was people checking if an expression was null, I'm going to say somewhere near a switch on that same expression. We tried to be relatively liberal in our definition of what near was. I think it was like within 3 nested blocks or 3 statements up or down, checking for that same expression is null or is not null somewhere in some if statement. And we thought this was a pretty good proxy for how many people would want to be able to do case null. There's a bias here that we're going to shout out right now. Google has a fairly null hostile culture. We try to recommend people avoid nulls. I'm not sure how successful we are, but that is a bias we thought we should own up to. So of nulls that we, null checks near switches, we found about 2.5% of switches checked for null somewhere near where the switch was happening. We also manually went and looked at that 2.5% and went, okay, are these people actually doing case null, what they intended to be a case null? And we can do that because we have the exact places in the code base and we can go and look at them. We can take a random sample and we can make some inferences about how many people are actually simulating case null. Kevin did that grunt work of looking at all of those. And so we came to the conclusion about 2 to 2.3% of switches are trying to simulate case null. And a majority of them, we don't have a ton of data here, so the confidence interval is fairly wide, but 60 to 80% of those are treating null the same as default, which we think is also actually pretty interesting.
Of course, the only reason that that confidence interval is so wide is I got really sick of manually reviewing them and I cut it off there. We can always narrow it by reviewing more and more and more.
Okay, what percentage of switch statements include fall through? The thing that always surprises new programmers, I'm going to claim. that if you omit a break, that your switch statement will just keep going. It will just keep going through the switch statement. At Google, we actually require that fall through be explicitly commented. This is both this increases, on the one hand, our confidence that fall through was actually intentional, that this is a measure of the people who actually wanted fall through. And on the other hand, it may discourage people from writing switches with fall through in the first place.
Louis, we should make them actually guess on this one.
Okay. Raise your hand if you think you have a guess. How many switch statements, a percentage of switch statements that actually involve fall through, not just case 1 colon, case 2 colon, which is we're treating as separate. People are trying to OR 2 cases. How many 2 guesses are doing an actual fall through?
15? 15% is one guess. Let's take at least one more so that we can pretend. And we have a guess of 5%. And? Well under 1. I actually don't know which of, go ahead.
I do. 2.4. 2.4% was the number we came out with.
Is it logarithmic or not? I didn't specify whether it's logarithmically closer or not. So.
Yeah, 2.4% were actually doing some non-trivial operation, and then at least one code path fell through to the next case. What do switch cases do? Since we were talking about expression switch in the first place, we went and found, okay, of all the switches, what are they doing? Are they, for example, assigning to the same variable in all cases? Are they all returning? Are they doing something more complicated? And we found roughly the blue and the green columns here represent switches that are being used roughly pretty obviously as an expression and could pretty clearly be replaced with an expression switch. The blue column is cases where all of the cases were assigning to the same variable. The green column is where all of the cases were returning, and these are pretty clearly refactorable to expression switch, even if they're not an exhaustive list of the expression valued.
Yes, so seeing this data makes us really want expression switch because we know it will apply to a lot of switch statements. So a couple other examples that we're not showing today just because. The first bullet, it was nice that there was a little shout out about this a couple sessions ago. Liam did method reference and lambda deduplication, but before we decided to go ahead and do that, we ran some analysis to figure out how often that would actually benefit the code. This is a teaser, we're not giving you all the numbers right here, sorry. Classes surrounding value, questions surrounding value classes, and getters, setters, constructors. And the last one, I took it out of the presentation because it was getting too long, but yeah, I was able to kind of show Jim some of the research we've done on that already. How many of our string literals would look like good use cases for migrating to raw string literals. Another thing that this whole process allows us to do, which haven't really embarked on yet, but we can, is we have a unique way of being able to collect subjective feedback as well about language features. In addition to just asking somebody in the abstract, just here's a feature, what do you think of it? We can randomly select code in the code base that looks like it's migratable, and we could send a little survey to the authors of those pieces of code. We could say, here is a change list that converts your code to use the new feature under this variation of how it's proposed, under that variation of how it's proposed. What do you think of the difference? And I think the more that people can express their opinions in some context, probably the better, as opposed to sort of just off the top of my head, I think I like A versus B. And another thing, of course, we can do is probe for understanding. Like, what do you think this does? Did you assume that what did you assume would happen if this were null? And things like that. So that's another possible future direction. I'm pretty pleased with how quickly we went through all this. We wanted to save as much time for questions in the hopes that, that you have some. Yes, takeaways. We have a large analyzable code base, and we are kind of like offering to do more analyses on it in ways that will aid library designers and language designers, sorry. And we would like to hear, we'll put our email address on the last slide, we'd like to hear what questions you might like to have answered from our code base. And I feel like I was going to say one other thing that I didn't put on the slide. I'll think of it while you're talking.
Yep. The other thing was just to encourage people to think about these sorts of data-based questions when you're considering language design. How many people would use it? Are there common cases among the potential users, and how common are those cases? Are existing solutions actually difficult to use, especially in measurable ways? Would this be popular if we refactored everyone we think could use this feature to use this feature? Would people be pleased using this language feature as opposed to what they were having to do already?
By the way, this is maybe a slight tangent, but we should point out that another way that we can use this ability is if Java starts releasing sort of experimental language features that are guarded by a flag, which has been discussed as a possibility. We are generally willing to use that flag and even refactor our code base to make early adoption of the new features so that we can get quality feedback from the code and from the users. Because if something has to be changed, we have the ability to refactor the code base again. We're generally willing to do kind of crazy things like that because we think that it could produce a type of feedback that has been sort of not possible to collect otherwise, before the feedback is too late. That's the end of our slides. I hope that we get some nice questions from the audience, starting with Jim.